Who doesn't love a good conspiracy? Who actually shot President Garfield? Did we really land on the sun? Does Finland exist? We might never know the real truth, but we can at least get one step closer by building a big bulletin board connecting all the clues with red string. And even if we can't learn the truth about birds, thanks to math, we can at least say quite a lot about how best to organize all that string. Today, we're learning about Fary's theorem. Let's explore. If you haven't seen one in your cousin's basement before, a conspiracy theory evidence board consists of a bunch of pieces of evidence connected by paths marked out by string. If you're trying to neaten up a conspiracy board, you might try to make it so that none of the strings cross each other, perhaps by rearranging the evidence. If that doesn't work, you might be tempted to try curving your pieces of string around each other with extra thumbtacks. Fary's theorem states that this will never help. If you can't clean it up with straight string, you also can't clean it up with curved string. In math words, any graph that can be drawn in 2D with non-intersecting curved edges can also be drawn using non-intersecting straight edges. This is a bit of a surprising result. We'll work our way up to an actual proof of this by the end of the video, but for now, let's start with why conspiracy boards are basically the perfect example for this theorem, and explain some terminology. On a conspiracy board, any two pieces of evidence have one piece of string running between them if they're directly connected, or no string if they aren't. There are no duplicate strings running between the same two pieces of evidence, and a single piece of string can't start and end at the same piece of evidence. To a mathematician, this looks exactly like a job for graph theory. In graph theory, a graph is a set of some number of vertices or nodes connected to each other by edges or links, with no loops from a vertex to itself, or duplicate edges between the same pair of vertices. On your conspiracy board, the vertices are the pieces of evidence, and the edges are the pieces of string connecting them. A graph doesn't have to be one connected unit, but if it is, we call it a connected graph. A board about a single conspiracy will probably be one of these. For the purposes of graph theory, all that matters is which pairs of vertices are connected by edges, not where you draw them on the page. So even if we rearrange the vertices, this is still the same graph, as long as we keep the same edges between the same pairs of vertices. A particular way of drawing a graph is called an embedding. So what if we want to make our conspiracy board have no intersecting strings? The equivalent question about a graph is whether we can draw it in 2D without the edges crossing. Such drawing is called a planar embedding, and a graph where this is possible is called a planar graph. For this graph of 4 points all connected to each other, for instance, we can just move one of the diagonals outside of the square. It turns out that not every graph is planar. For instance, if we have a graph of 5 points all connected with all possible edges, named K5, the best we can do is get it down to one crossing. You can try it for yourself. So if your conspiracy board isn't planar, you're out of luck. Some of your strings are just going to have to cross each other. But what if it is planar? String has an extra restriction. It can only go in straight lines, unless you wrote it around using thumbtacks. This is where we return to Fary's theorem. Using the words we just learned, the theorem states that every planar graph has a planar embedding in which all the edges are straight. So you don't need the extra thumbtacks at all. For our square graph, for instance, we can rearrange it like this. We can try as many examples as we want, but we want to prove that this works for every possible planar graph. How do you prove something for infinitely many examples? One great math tool for this is called induction. The way we'll use induction in our proof is to start by showing that Fary's theorem, or actually a slightly stronger version of it, holds for every planar graph with at most 3 vertices. Then we'll show that once you know that the upgraded version of Fary's theorem holds for graphs with up to a certain number of vertices n, the result also holds for graphs with n plus 1 vertices. Thus, since we know it holds for graphs with up to 3 vertices, we can deduce it must hold for graphs with 4, and then 5, 6, 7, and so on for any finite number. We'll leave infinite planar graphs alone, at least for this video. A graph with no vertices is entirely empty. One with 1 vertex is just a single point, one with 2 vertices can have 1 edge or no edge, and one with 3 vertices can either make a triangle or a triangle missing some edges. All of these can be drawn with straight lines, so Fary's theorem works for graphs with up to 3 vertices. We're off to a great start. Now comes the other half of the proof, the induction step, showing that if the theorem holds for n vertices, it also holds for n plus 1 vertices. Here's what the process looks like visually. We start with a planar embedding of a graph with n plus 1 vertices, then we remove one vertex with at most 5 neighbors. We reconnect some of those neighbors, and find a straight line planar embedding of the modified graph with n vertices. Then we add the missing vertex back in, and redraw the appropriate edges. Seems easy enough. The hard part is proving that each of those steps is always possible. So, let's take a planar graph with n plus 1 vertices and call it G. Since we've already proved n up to 3, we can assume n plus 1 is at least 4. To make our job easier, let's add edges to G, possibly curved ones, until it's connected and we can't draw any more edges without a crossing. We'll call the new graph, a so-called maximal planar graph, G1. If we can find a straight line planar embedding of G1, we can remove the appropriate edges and get a straight line embedding of G. Adding these extra edges is helpful because maximal planar graphs have some additional useful properties compared to non-maximal planar graphs. In particular, notice that all of G1's faces, that is, regions of the plane marked off by the graph's edges, including the outside one, are bounded by exactly 3 edges. This is because it takes at least 3 edges to define a face, unless you have fewer than 3 edges in the whole graph, and if a face had 4 or more edges, we could draw a diagonal across that face, splitting it into 2 different 3-sided faces, and we would have done so in the process of making G1 maximal planar. Here's where we upgrade the theorem, which will help us later. For any maximal planar graph like G1, we can find a straight line embedding with any chosen face as the outside one that preserves the vertices, edges, and faces of whatever planar embedding we started with. For the 3-vertex maximal planar graph, there's only 2 triangle faces, so we can just pick one to be the inside and one to be the outside as we please. So we know the upgraded theorem holds for n equals 3. Now it's time to go about proving that each of our steps is always possible. The first one's the hardest. We have to show that at least one vertex of G1, excluding the 3 we picked to be on the outside, connects to 5 or fewer edges. The number of edges on a vertex is called the degree of the vertex, so we're looking for a vertex of degree 5 or less somewhere on the inside of G1. There's another tool we need to do this, Euler's formula for planar graphs. The formula states that the number of vertices of a planar graph V minus the number of edges E plus the number of faces F equals 2. You might have seen this before as a formula for convex polyhedra, but it works equally well for planar graphs, and many of the same proofs apply to both cases. We'll just take this formula as a given here. Since all the faces of G1 have 3 edges, and each edge is between 2 faces, G1 has exactly 3 edges for every 2 faces, or in a formula, 1/2 F equals 1/3 E. Now we do some algebra with this fact and Euler's formula. This gives us that the number of edges E is 3 times the number of vertices V minus 6. The sum of the degrees of all the vertices is the number of times in the graph where an edge meets a vertex. Since every edge on a graph goes between 2 vertices, this is 2e, or 6v minus 12. So we know the sum of all the degrees of all the vertices in the graph together is 12 less than 6 times the total number of vertices. This means some vertices in the graph must have 5 or fewer edges. If they all had 6 or more, the sum of the degrees would be at least 12 too big. How do we know that one of those vertices is on the inside? Define the deficiencies of a vertex as 6 minus its degree. We have a total of 12 deficiencies to spread over all the vertices of G1. Suppose all 12 of those deficiencies were taken up by the 3 outer vertices. That means that among those 3 vertices, there would be 3 times 6 minus 12 total connections, which is 6. But the outer triangle itself has 6 connections. So if there's even one vertex on the inside, which G1 must have, there would be no connections left to link it with the outer 3 vertices, making the graph not maximal planar. Therefore, at least one deficiency must be on the inside of G1, so at least one vertex inside G1 has 5 or fewer neighbors. Okay, we've proven the first step is always possible, and we can remove a vertex V with 5 or fewer neighbors, while still keeping any triangle we want on the outside. The next step is to reconnect the neighbors so the graph stays maximal planar, which we can do with curved edges if we have to. Now we get a new graph, G2, which is maximal planar with only n vertices. By the assumptions of the induction step, we can draw a straight line planar embedding of it, keeping the same outer triangle. If we then remove the added edges, we end up with all the neighbors of V, of which there are at most 5, surrounding a single face that isn't the outside one. Now we just need to show that we can add V back and connect it up with straight lines. This comes from geometry. It turns out there is always a point on the interior of any triangle, quadrilateral, or pentagon that can be connected to all the vertices with straight lines running through the interior of the shape. These are all the distinct cases. Note that this isn't true for, say, this concave hexagon, so it's important that V has 5 or fewer neighbors. So that means our induction is done. Starting with any finite planar graph, we add edges to make it maximal planar, then remove vertices until it's down to just the outer 3, add the vertices in again one by one, and finally remove the extra edges, and we have a straight-edged planar embedding. So there you have it, that's the proof. If you want to ponder just a little more math, here's a question. Is it always possible to find a straight line embedding of a planar graph where all the edges have integer lengths? Turns out, no one knows for sure. This is called Haworth's conjecture, and it is as yet an unsolved problem. Maybe you can find out the real truth with a newly well-organized evidence board of your own, just as soon as you figure out the whole Finland thing. And as always, thanks for watching.